Welcome to this screencast, fairly short screencast on the idea of recursion. This is the last section that we'll be talking about out of the textbook, and recursion is, just want to get you an introduction to what recursion is and how it works. So recursion has two pieces. One is it can be thought of as defining something in terms of itself, and this is not insane. Doing the same thing again and again and again and expecting a different outcome is often called the definition of insanity, but in recursion we do that, but we're not doing exactly the same thing again. And so when we talk about defining something, you might say something like an ancestor is either a parent or an ancestor of a parent. So that gives you this idea that you're defining the term ancestor sort of infinitely back. So it's your parent or your parent's parent or your parent's 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 parent. And this way of defining it doesn't mean you have to do exactly how many times back you go for ancestor. You can say a sentence can be, among other things, two sentences joined together by a conjunction, such as and or. So that's, again, you're giving some specifics about a sentence, but it's in terms of sentences. But here we're talking about you have two sentences joined together by a conjunction. So that is a sentence. But you still haven't totally defined what a sentence is in this case. Or a directory is a part of a disk drive that can hold files and directories. So here again, you're saying that a directory can hold files, but it could also hold directories. So we can do this idea of defining something that it holds files or it holds things that are like itself. And you can imagine the directory tree, which has directories inside of directories and inside of directories. And finally, at the leaves, you only have files. But this is a very nice and somewhat concise way of defining some very sort of abstract ideas. You can't define all your ancestors going back until the first ancestor. We just don't know enough back, but this definition gives you something very concise and does actually handle all those cases. So that's one thing. You can use recursion to define things in terms of self. It's often used later on in data structures. You might say a linked list is a node that has a linked list following it. Something like that. You'll learn that next semester in ICS 211. We can also have a programming or problem-solving technique where we can have a recursive method or a recursive subroutine, and the definition of a recursive method is a method that calls itself. And there's two ways of doing this. There's either direct recursion, which we have a method in foo that does some stuff and then returns a call to itself. So foo is going to call foo. Now the do the stuff is where we don't do this forever. The do the stuff will make some decisions and stuff. But this is direct or directly recursion. The indirect way is you have a method, for example foo, that calls another method, and that other method eventually calls foo. So we go back to the foo to begin. And this indirect recursion doesn't necessarily have to be just one method call. You can imagine foo calling bar, which calls baz, which calls foo, or a long chain of calls that eventually at the end will call back to foo, and that can get very confusing and very difficult to trace as to what's going on. But so recursion allows us, or with methods allows us to call itself, and then when foo eventually returns, bar will return, and then the first call of foo will return. So it can be confusing, but when you return, we come back and we eventually get back to the first call. So recursive problem solving, the idea is you have a problem and you can break the problem into smaller problems. And you do the same thing when you're breaking the problem down. You break the problem down, you break the problem down until you find a problem that you can solve right away. You know the answer. There's something there. That's the smallest one. We know there's something there. And then we combine the results from that simplest one with the previous breakdown, and then we combine it again, and then we combine it again until we've solved the entire problem by breaking it down into smaller problems, solving the simplest one, and combining the results back to the top. So we can have a generic recursive algorithm. If you can solve the problem for a value n, you solve it. That's the answer. If you can't, or else you can't solve it for n, recursively apply the algorithm to smaller n's. So we're trying to break the values of n until they're small enough that we can simply solve it. Then we combine the solutions from all those steps to solve the original problem n. So the idea is if you have this simple solution, you solve it, or you recursively do the problem until we get to that simple solution, and then we combine all those solutions back to solve the big problem. So we talked a couple last week about binary search, where we search the thing in the middle, and then we search the left side, and or we search the right side, depending on if the thing is left or right or larger than the middle. So here's the algorithm is if there's no list to search, the value wasn't there. We're done. If the value is in the middle, or if the thing we're done, and we turn the middle index. If the value is less than the middle item, we search the left half, which sounds very recursive. If the value is greater than the middle, we search the right half. So we're doing a search, and each time we do the thing. So let's step through this recursive binary search. So the first step is if it's not there, we're done. So if low index is greater than high index, that means we swapped them over, and we've looked at the whole thing, or all the pieces, and the item's not in the array, so we return -1. This is a base case. This is an easy solution. It's not there, right? It's not there. We can return -1. We solved the problem. The next is if the value is equal to the middle, so we calculate the middle. We check the middle against the value, and if it's the one we're looking for, easy solution. There's no work. We just say, hey, we're done. We return the middle. So we didn't do anything. We have two base cases here. If we don't have a list or a list, we return -1. If we find the thing at the middle, we return the middle. Else, we say if the value is less than the middle, then we need to search to the left. So we call binary search again, supply the same array, the same low index, but now we want the left side of middle, so that's why it's middle -1, and we're still looking for value. So we're now looking at the left-hand side of the piece of the array that we were looking at. And we call binary search, which will go back to the top, and we'll start to call it again. If value is less than, if not less than middle, then we return binary search, and we're going to look at the right-hand side of the range we're looking at. We still pass it A. We go middle +1, and then the high index, because that's the right-hand side of the thing, and we're still looking for value. So either we'll get to the case where the item's in the middle, and we return the middle index, or because we say middle +1 or middle -1, depending on if we're searching left or right, we will swap the high and low index, and so we will hit our base case. So there's no way to run this search where we don't hit the first base case where we've searched everything, or we actually find the thing. So this recursive binary search does not have infinite recursion, because the way we're making the problem smaller, we're guaranteed to either have we run out of array or we find it. So we can talk about correct recursion by saying you must have one or more base cases that can be solved without recursion. Those are the simple solutions that we don't have to do any more work. We solve the problem. Or if we don't have a base case, then we use recursion to solve a smaller problem. So how do we shrink the problem? In the binary search, we search a smaller piece of the array. And since one of the base cases is there is no high and low of swapped, that gets us to a base case. So that shrinking the problem must reduce the problem to one of the base cases. If it doesn't, we can end up with infinite recursion, which means we just keep calling ourselves until finally we run out of memory, because every method call puts a record on an activation stack, And so eventually we'll run out of space because the stack would keep filling up with all these activations of our recursive calls, and we'll run out of memory and the program will crash. So it's important when you're talking about recursion to guarantee that you have at least one base case. You saw in our binary search we had two. You can have more than two. And a recursive call that shrinks the problem. So often you search or you look at a smaller set of things, you go towards the end of something, you try all the, if you're searching a maze recursively, you're at some point you have no more choices, so the problem gets smaller. So you need base cases and a recursive call that is applied to a smaller problem. So let's talk about some classic recursive problems or problems that can be solved. One of the classics is the Tower of Hanoi problem. You have a stack of disks of smaller and smaller sizes, basically your tower, and you have to move all the disks from one stack onto stack 1. So you're moving them all from stack 0 to stack 1. You can use stack 2 as a temporary location. You can move things. The rule is you can only move one disk. Only the top disk may be moved, and no disk may be placed on a smaller disk. So you can't put a larger disk on a smaller disk. So what's the solution? Well, you see that we could, if we moved n-1 disks to stack 2, and then we moved the nth disk, the largest disk, to stack 1, and then we moved the n-1 disk from stack 2 onto stack 1, we have solved the problem. Notice that it's a slightly smaller problem, n-1. So eventually we'll get to the place where n is 1, and if we look at that, 0 disks to stack 2, okay, don't do anything. Move the 1 disk to stack 1, and move the 0 disks from stack 2 to stack 1. So the base case is we have 1 disk, we move it from stack 1 to stack 0 to stack 1. So that's our base case. So now let's look at this in code. If disks equal 1, base case, we move that 1 disk. Easy peasy, done. Else, we move the n-1 disks from the start disk to the spare disk using the 2 disks, this target disk where we want to go to, as our extra space. So that's the move n-1 to the spare disk, and we have the recursive call. We then move our nth disk from stack to stack, the from and to, and then we have the recursive call to take it from the spare stack to the destination, and we have the from disk as our location where we can move stuff. So that's our recursive call. That solves the Tower of Hanoi problem. And you can see how in code you can take that description and quite easily say, well, if we only had 1 disk, we move the disk. That's our base case. Else we recursively move the n-1 disks from where we are to the spare using the goal disk, our goal stack is our extra space. We then move the 1 disk. We then move the n-1 back from the spare onto the target, and we're done. So there's 2 recursive calls here. The first one, then we move the disk, and then the second one. And eventually that will solve the problem. In the text, you can cut and paste the code and watch the Tower of Hanoi's animation. It's actually quite interesting to see all those things. The animation of how you move the disks and they keep bouncing around. But it does work. It takes a little while, but I highly recommend you take a look at the code from the text and run it in Eclipse to see how it works. We can also use, we talked last week about sorting. There are recursive ways to do sorting. And there's one specific one called the Quicksort, which is a fairly quick recursive sort that basically has this idea of you select a pivot value, and then all you do is you're swapping values that are smaller than this pivot value to the left, and you move all the items larger than the pivot value to the right. So in effect, you're making the pivot value go to the right place in the array that you want it to be, and then you recursively sort the stuff to the left of the pivot, and you recursively sort the stuff to the right. So it's a recursive sort that you basically just swap things around so that all the things lower than the pivot are to the left, and all the things are higher that are right. They don't have to be in order. They just you have to put the lower ones to the left and the higher ones to the right. So here's sort of the first step in the recursion where we're swapping things back and forth. We pick a pivot that is at the low point. We could pick the pivot anywhere. We're just arbitrarily picking it on the low point. We then, while low is greater than high, because that knows we've swapped everything, while high is greater than low, that's to make sure that we don't move past each other, and high is greater than or equal to pivot. Well, 18's not, so we don't do anything. This just indicates we're done. If it's not there, we want to swap the thing in high to low. And notice we sort of make space in high because we pulled the pivot out, so we have space at low. And then we move low up. So we know that 18 is less than 23. It's going to be to the left of where 23 ends up. We moved up. So now we want to check to see if low is less than pivot. We can increment low. So we did. We went from 10 to 7. We go again. So we're now got a 45. A sub low is not less than pivot. So we check to see, are we done? Nope. So we swap that 45 to make sure it's bigger than the pivot. We move it to the right. We then move the high down. We're done with this body of the while loop. Are we finished? No, we're not finished. Again, we check to see, is high greater than the pivot? 2 is not greater than the pivot, so we don't increment high. We're not done. We swap the 2 to the left side. We increment the pivot. Is 16 less than 23? Yes, so we increment it. Is 86 less than 23? No, so we're done. Is high equal low? No. So we swap that 86 to where high was. So now we decrement high, done with the body of the outer while. Is 56 greater than the pivot? Yes, we decrement high. Is high greater than low? No, they're equal, so we break out of the while loop. Is high equal low? Equal low? Yes, we're done. So we have found where the pivot belongs. Break out of the outer while loop. Insert the pivot into low. That is the correct location for 23 in the sorted array. So now that we've done that, we've moved all the things that are left of it, less than 23 to the left, all the things greater than 23 to the right, and notice they're not sorted, but we now have sort of sorted the array. We now can sort the left-hand side, and we can sort the right-hand side using the same swapping mechanism. So that's the idea behind the quicksort. We move all the things less than the pivot to the left, move all the things to the right, greater than the pivot to the right, and then we just sort each one. So here's the quicksort algorithm. If high is less than or equal to low, we're done because we've gotten to the point where we're sorting either one thing or we've swapped over each other. And one thing is sorted naturally, else we do that quicksort step to move everything to the left and the right of the pivot correctly. We then quicksort and we return where the pivot value belongs. We then quicksort A from the low position to the pivot pos -1, which is the left-hand side of the array. And then we quicksort the right-hand side, which is pivot pos +1 to high. And then we can write the wrapper method that just takes an array. We quicksort from 0 to a.length -1. That is the quicksort. So we have the quicksort step, which shifts the things around and returns where the pivot belongs. And then we just recursively sort the left side, recursively sort the right side. And because it's trying to divide the problem in halves, and it generally does do a good job, it makes the problem much quicker than sorting using either the insertion sort or the selection sort, because we had to look at everything twice. Basically, we did two inner loops, whereas the quicksort is dividing the problem into smaller and smaller pieces. So that makes it quicker than the insertion or selection sort. So that's a quick review of recursion, or introduction, I shouldn't say review, it's an introduction of recursion. It's a very powerful way of solving problems or defining things. As we said, your ancestor is your parent or your parent's ancestor. And remember, when you're doing recursion and you're doing it as a problem solving, you have to have one or more base cases that can be solved without recursion easily. And a recursion is applied to a smaller problem that reduces the problem to or toward one of the base cases. If you don't do that, you're going to have infinite recursion, and if you're running a program, eventually you run out of memory and it'll crash. So that's a quick introduction to recursion. Very powerful problem-solving technique, but sometimes maybe a little difficult to wrap your head around, where you're going to call the same method again and again and again and eventually get a different answer. So it's not insane. It's just a really cool, it's a really powerful way of solving problems. Thank you.